So we're beginning our next section of Chapter 10, 10.6, alternating series. Up until now, what we've been looking at have been series that had all positive terms, and now we're going to look at series that have alternating polarities of terms. There are, as this says, our previous discussion focused on infinite series with positive terms, which is certainly an important part of the entire subject. But there are many interesting series with terms of a mixed sign. For example, the series 1 plus 1/2 minus 1/3 minus 1/4 plus 1/5 plus 1/6 minus 1/7 minus 1/8 plus etc. has the pattern that two positive terms are followed by two negative terms and vice versa. Clearly, infinite series could have endless sign patterns, so we need to restrict our attention. Fortunately, the simplest pattern is also the most important. We consider alternating series in which the signs strictly alternate, as in the series, the sum from k equals 1 to infinity of negative 1 raised to the power of k plus 1 over k equals 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, etc. The factor negative 1 raised to the power of k plus 1 or negative 1 to the k has the pattern 1, negative 1, 1, negative 1, and provides the alternating signs. Let's see what is different about alternating series by working with the series, the sum from k equals 1 to infinity of negative 1 raised to the power of k plus 1 over k. This is called the alternating harmonic series. Recall that this series without the alternating signs, the summation from 1 to infinity of 1 over k, is the divergent harmonic series. So an immediate question is whether the presence of alternating signs affects the convergence of a series. If we investigate this question by looking at the sequence of partial sums for this series, in this case, the first four terms of the sequence of partial sums are when k equals 1, 1. When k equals 2, we get 1 minus 1/2, which equals 1/2. When k equals 3, we get 1 minus 1/2 plus 1/3 equals 5/6. When k equals 4, the sequence of partial sums is 1 minus 1/2 plus 1/3 minus 1/4, which equals 7/12. If we plot the first 30 terms of the sequence of partial sums results, we get this figure. The terms of the sequence of partial sums appear to converge to a limit. If they do, it means that while the harmonic series diverges, the alternating harmonic series converges. We will soon learn that taking a divergent series with positive terms and making it an alternate series may turn it into a convergent series. For series with positive terms, the sequence of partial sums is necessarily an increasing sequence. Because the terms of an alternating series alternate in sign, the sequence of partial sums is not increasing. For the alternating harmonic series, the odd terms of the sequence of partial sums form a decreasing sequence, and the even terms form an increasing sequence. As a result, the limit of the sequence of partial sum lies between the two consecutive terms of the sequence. I think that's pretty logical as we think about that, right? Every other term is negative or positive, and so if we just take all the positive terms, then it's increasing, etc. We now consider alternating series in general, which are written in the summation of negative 1 to the k plus 1 times a sub k, where a sub k is greater than 0. With the exception of the divergence test, none of the convergent tests for series with positive terms applies to alternating series. Fortunately, one test works for most alternating series, and it's easy to use. The alternating series test, Theorem 10.16. The alternating series test, the summation of negative 1 to the k plus 1 power, a sub k, converges providing the terms of the series are non-increasing in magnitude. That is, that 0 is less than a to the sub k plus 1, which is less than or equal to a sub k, for k greater than some index n, and the limit as k goes to infinity of a sub k equals 0. There is some potential for confusion here. For series of positive terms, the limit as k goes to 0 of a sub k equals 0 does not imply convergence. For alternating series with non-increasing terms, this does imply convergence. Next, we look at the proof of the alternating series test. And it's pretty short and instructive, and it relies on figure 1035, which you see below. We considered an alternating series in the form of the sum from k equals 1 to infinity of -1 raised to the power of k plus 1, the alternating effect, times a sub k sequence. So this equals a sub 1 minus a sub 2 plus a sub 3, etc. Because the terms of the series are non-increasing in magnitude, the even terms of partial sums s sub 2k equals s sub 2 plus s sub 4 plus s sub 6, etc. These form a non-decreasing sequence that is bounded above by s sub 1. By the bounded monotonic sequence theorem, section 10.2, the sequence has a limit, and we're going to call it L. Similarly, the odd terms of the sequence of partial sums, s to the sub 2k minus 1, equals s sub 1 plus s sub 3 plus s sub 5, etc. These form a non-increasing sequence that is bounded by s sub 2. By the bounded monotonic sequence, this sequence also has a limit that we're going to call L prime. At the moment, we cannot conclude that L equals L prime. However, notice that S sub 2k equals S sub 2k minus 1 minus A 2k. By the condition that the limit as k goes to infinity of A sub k, it follows that the limit as k goes to infinity of s sub k equals the limit as k goes to infinity of s sub k 2k minus 1 minus the limit as k goes to infinity of a sub 2k. And if you notice here in the blue, you'll see that is saying that L equals L prime minus 0. Okay? And this was the condition that we had from the last theorem. 1016, the alternating series test. Okay? Therefore, the sequence of partial sums converges to a unique limit, and the corresponding alternating series converges to that limit. Using what we just saw from the last proof, the fact follows immediately from the alternating series test, because the a sub k equals 1 over k decrease, and the limit as k goes to infinity of a sub k equals 0. Therefore, we have theorem 1017, alternating harmonic series. The alternating harmonic series converges even though the harmonic series made up of just positive members diverges. So let's look at our first example. Determine whether the following series converge or diverge using the alternating series test. So I just put theorem 1016 here again. So you remember what we're trying to do is prove these two postulates, okay? So an alternating series converges if, first of all the terms of the series are non-increasing in magnitude. And, this is an and, not an or, and the limit as k goes to infinity of a sub k, whatever our function is here, has to equal 0. So keep those two things in mind when you're doing these tests to see if alternating series converge. When we look at A, we can see that as we increase k's value above 1, that all of the members of 1 over k squared, and remember we take out this, a sub k is just the function that is left by taking out the alternating polarity function. So we're looking at 1 over k squared. So when k is 1, we have 1. When k is 2, we have 1/4, 3, 1/9, etc. So we can see that it is definitely decreasing in magnitude. Now, if we apply the limit as k goes to infinity, again, just of the function that represents a sub k, which is removing the alternating function, we can easily see that this goes to 0. So both of the conditions are met, and so this series converges. If we look at series B, or the question B, and we use sigma notation, we can rewrite this as k plus 1 over k for our sequence, okay? Because the limit as k goes to infinity of k plus 1 over k equals 1, the sequence, -1, this sequence, I'm not going to go through that again, oscillates and diverges. Remember, it has those two conditions. They have to be decreasing in nature, and the limit as k goes to infinity of a sub k equals 0. And so this function diverges by the divergence test. Finally, let's look at the last one, and this is an interesting case. Part C, again, the first step is to show that the terms decrease in magnitude after some fixed term. And again, here we're looking at the function, the natural log of k over k. So the approach here is quite interesting. One way to proceed is to look at the function f of x equals the natural log of x over x, which generates all the terms in the series, right? By the quotient rule, if we take the derivative, in order for these terms to become smaller, then the derivative, which represents the slope, needs to be going down, or I should say the derivative needs to be negative. The fact that the derivative is negative for x greater than e implies that the terms, the natural log of k over k, decrease for k greater than or equal to 3. As long as the terms of the series decrease for all k greater than some fixed integer, the first condition of the test is met. And that's an important note here in this example. As long as the terms of the series decrease for all k greater than some fixed integer, the first condition of the test is met. It doesn't have to start at k equals 2, which you can see here is even less than e, of course, Euler's constant. Okay? Furthermore, using L'Hopital's rule, or the fact that the natural log of k increases more slowly than k, we see that the limit as k goes to infinity of the natural log of k over k does equal 0, and therefore, by the conditions of the series tests 1 and 2, this series also converges. So those were 3 really good examples, and you might want to rewind a little bit and walk through those again so that you get them. Recall that if a series converges to a value of s, then the remainder, r sub n, is equal to s minus s sub n, where s sub n is the sum of the first n terms of the series. The magnitude of the remainder is the absolute error in approximating s by s sub n. An upper bound on the magnitude of the remainder in an alternating series arises from the following observation. When the terms are not increasing in magnitude, the value of the series is always trapped between successive terms, above and below, of the sequence of the partial sum. Therefore, as we can see in the figure below, the absolute value of R sub n is equal to the difference between the absolute value of the difference between S sub n and S. Here's the value of the series S and then S sub n. The absolute value of this is less than or equal to S sub n plus 1 minus S sub n. So if we go one further, right? And of course, this value is going to equal the value of the next member, A sub n plus 1, or what we call the first neglected term, the first term after using some value of n where we're going to stop. This is a very common use in engineering because often you're trying to create something within some error rate, some level of error, so that you get close enough that you meet some constraints, etc. And so this leads us to theorem 10.18, the remainder in alternating series. Let the sum k equals 1 to infinity of negative 1 k plus 1 a sub k be a convergent alternating series with terms that are non-increasing in magnitude. Let R sub n equal S minus S sub n be the remainder in approximating the value of the series by the sum of its first n terms. Then the absolute value of R sub n, the remainder, is less than or equal to A sub n plus 1. In other words, the magnitude of the remainder is less than or equal to the magnitude of the first neglected term, which is basically just the next term once we've defined how far out we're going to go. This will become a little bit more clear as we look at the next example, example 2. So it turns out, interestingly, that the natural log of 2 equals 1 minus 1/2 plus 1/3 minus 1/4 plus etc., which is the sum from k equals 1 to infinity of negative 1 k plus 1 all over the quantity of k. So we have an alternating series here of 1 over k. How many terms of the series are required to approximate the natural log of 2 with an error less than 10 to the negative 6? The exact value of the series is given, but is not needed to answer this question. Okay? So we can see that the series is expressed as the sum of the first n terms plus the remainder. This is from the last theorem. Okay, right? So here we have S sub n, and then here we have the remainder R sub n, which is the difference between S and S sub n, which is less than or equal to the next term. Okay? Well, remember our A sub k, looking at this, is our function without the alternating function, so it's just 1 over k. Okay, so A sub k equals 1 over k. All right? Remember from our theorem that this remainder, the absolute value of the remainder, is less than or equal to A sub n plus 1. Well, if A sub k is 1 over k, then A sub n plus 1 is 1 over n plus 1. And here we were trying to find an error less than 10 to the negative 6. So since our error has to be less than 10 to the negative 6, right? 1 over n plus 1 is the absolute value of our remainder, and we want that to be smaller than 10 to the negative 6. Well, of course, 10 to the negative 6 is 1 over 10 to the 6, so we can set the denominators in a way that n plus 1, again, we now have to flip it since we're flipping the functions, right? We're taking the reciprocals, basically, of each function. So the inequality changes direction. So now we have n plus 1 has to be greater than 10 to the 6. Well, 10 to the 6 is 1,000,000, so we have to have 1,000,000 terms of the series in order to approximate the natural log of 2 with an error less than 10 to the negative 6. In example A, we were trying to find how far in the series we had to go to meet a certain condition of error rate. So we wanted to see how far we had to go to make the error less than a certain value. Here we're trying to detect the error rate the upper bound of the error rate, the biggest size of the error, after going a specific number of terms. Okay, so let's look at that. Consider the series -1 plus 1 over 2 factorial minus 1 over 3 factorial plus 1 over 4 factorial, which equals the sum of the alternating factor, -1 to the power of k, all divided by k factorial. Find an upper bound for the magnitude of the error in approximating the value of the series. It gives you the fact that the value of the series is e to the -1 minus 1. So that's kind of helpful here. And specifically with n equals 9 terms. Okay. So again, this series can be expressed as the sum of the first 9 terms here plus the remainder, the next term. Okay. The error committed when using the first 9 terms by the theorem 1018 is equal to s minus s sub 9, because we indicated that we wanted 9 terms, which of course is less than or equal to a to the n plus 1, which in this case would be a to the 10. Okay, well, a to the 10, again, our function here is 1 over k factorial once we remove the alternating function. Okay, so we get 1 over 10 factorial, which is 2.8 times 10 to the -7. All right, therefore the error can be no larger than that. It has to be less than or equal to by our theorem. And as a check, the difference between the sum of the first 9 terms, if you plug this in, is -0.6321, etc. And the exact value of s equals e to the -1 minus 1 is -63212, etc., which is approximately 2.5 times 10 to the -7, which is smaller than what we see here. Okay? So these are two different kinds of ways of looking at the problems. One is to figure out how far in the series you have to go to meet an error constraint. The other is to find out the upper constraint of the error by indicating a specific number of terms. In this final segment, we're going to introduce some terminology that's going to be needed in Chapter 11. We now let the notation the summation sigma a sub k to denote any series, a series of positive terms, an alternating series, or even a more general infinite series. Look again at the convergent alternating series, harmonic series, -1 to the k plus 1 over k. The corresponding series of positive terms, the summation of, or sigma of 1 over k, is the divergent harmonic series. In contrast, we saw in example 1a that the alternating series converges, and the corresponding p-series of the positive terms, 1 over k squared, also converges. These examples illustrate that removing the alternating signs in a convergent series may or may not result in a convergent series. The terminology that we now introduce distinguishes between these cases. As you can see in green here, the absolute and conditional convergence definition. If sigma of the absolute value of a sub k, so these are all positive terms, if this converges, then sigma of a sub k, the summation of a sub k, the series, converges absolutely. However, if the absolute value or the positive terms diverge and the non-absolute value, positives, negatives, alternating, etc., converges, then we say that the series converges conditionally. So let's look at some convergence examples. The series sigma -1 to the k plus 1 over k squared is an example of an absolutely convergent series because the series of absolute values simplifies to the summation of 1 over k squared, which we can easily see that this is a convergent series converging to 0. In this case, removing the alternate signs in the series does not affect its convergence. On the other hand, the convergent alternating harmonic series, sigma -1 to the k plus 1 over k, has the property that the corresponding series of absolute values does not converge. In this case, removing the alternating signs in the series does not affect convergence. So this series does not converge absolutely. Instead, we say it converges conditionally. A convergent series such as the alternating harmonic series may not converge absolutely. However, if a series converges absolutely, then it converges. Okay, a little bit confusing, so let's look at the next slide and hopefully kind of give you an overview of this convergence definition and thoughts, etc. And I've put the definition on this slide too, so you can see that. So we're saying that if the absolute value converges, then it converges absolutely. If the series diverges, if the absolute value diverges and the regular series converges, then it converges conditionally. And those were what those two examples are. So I think the flow chart here to the left, figure 1037, gives an overview of absolute and conditional convergence in a simple way. So we can see here that when we have an infinite series, what we're first asking is, does it diverge or does it converge, right? We've been doing that throughout this entire chapter. So once we know it converges, then what we're going to do is figure out if it converges absolutely or conditionally. And we do that by looking at the infinite series with only positive values, etc. So here it is in kind of words, okay? Figure 1037 gives an overview of the absolute and conditional convergence. It shows the universe of all infinite series split first according to whether they converge or diverge. Convergent series are further divided between absolute convergent and conditionally convergent series. Okay, here's a few more conditions. The distinction between absolute and conditional convergence is relevant only for a series of mixed signs. Okay, the distinction between absolute and conditional convergence is relevant only for a series of mixed sign, which includes alternating series. If a series of positive terms converges, it converges absolutely. Conditional convergence does not apply. To test for absolute convergence, we test the series absolute value, as we saw up here in our definition, which is a series of positive terms. Therefore, the convergent test of sections 10.4 and 10.5 for positive term series are used to determine absolute convergence. Okay, I'm hoping that didn't confuse things more, but that it actually helped understand what's going on with this absolute and conditional. So let's look at our final example, example 3, determining absolute or conditional convergence. Absolute and conditional convergence. Determine whether the following series diverge, converge absolutely, or converge conditionally. Let's look at part A. The series from k equals 1 to 1 of -1 to the k plus 1 over the square root of k. So here we have the a sub k function of the sequence is 1 over the square root of k, right? Once we take the other function out. Now, the function without the absolute value is a divergent p-series with p equals 1/2, which is less than 1. Therefore, the given alternating series does not converge absolutely. Okay. To determine whether the series converges conditionally, we look at the original series with alternating signs. And I've put the theorem 1016 down here. So remember what we're doing here is we're trying to figure out if the limit as k goes to infinity of a sub k equals 0. And that's what we have here. And we can see that it indeed does go to 0. So this series does converge, but since the alternating series diverges, it doesn't converge absolutely, okay? So now let's look at part B. The series of 1 over, the alternating series of 1 over the square root of k cubed. So again, to assess the absolute convergence, we look at the series of the absolute values. And so when we apply the absolute value here, we get 1 over k to the 3/2. This is a convergent p-series with p equals 3/2, which is greater than 1. Therefore, the original alternating series converges absolutely. So both of the series converge, and so it converges absolutely because this absolute value series converges absolutely. Okay. So here we have part C is the sine of k over k squared. And the terms of the series do not strictly alternate in sign. The first few signs are positive and then followed by negative, as we know that sine goes between 1 and -1. So the alternating series does not apply. Because the sine of k, the absolute value of the sine of k, is less than or equal to 1, the terms of the series of the absolute value satisfies this. So we know that k squared is going to be positive, so we can take the absolute value out of there. The absolute value of the sine of k is going to be, as we just said, is going to be less than or equal to 1. So we have this function here, 1 over k squared, which is a convergent p-series. Therefore, by the comparison test, the series, the absolute value of the sine k over k squared converges, which implies that this series converges absolutely. And by 1019, it converges. Okay. Finally, our last example is part D. And here we can apply the limit as k goes to infinity of k over k plus 1, which is our a sub k, right? Taking out again, the alternating function. And when we see that, we can see that this goes to 1. And this is one of the reasons why I put the first theorem on there, or 1016 on here. Since this doesn't equal 0, this implies that the sequence oscillates and diverges. The terms of the series do not tend to 0, and by the divergence test, the series diverges. Okay, so there you've had 4 different examples and ways of looking at them, and hopefully that will help you with your homework and help us as we move into chapter 11.